Hello folks, welcome back to Merrill Math. I'm Mr. Merrill. Today we're going to be talking about explicit and recursive rules for exponential tables. Now in my last video we discussed linear tables and what those relationships look like. So our exponential tables are going to have a little bit of a different relationship, but luckily it's kind of an easy one to spot. So we're going to get into talking about explicit and recursive rules for those, but the first thing we have to do is tell when are we dealing with an exponential table. So how do we know when a table represents an exponential relationship as opposed to a linear one or a quadratic one or a cubic one? So if we have these numbers here, we might be inclined to start looking at the differences between these. But as we can tell, this goes from an output of 2 to an output of 162 in 4 steps. This is very, very rapid growth. And that's sort of where the phrase exponential growth comes from. So we can see that this is increasing very rapidly, but it's not increasing in equal steps. So from 2 to 6, that is an increase of 4. Here is an increase of 12. Here is an increase of some other number. So we're not looking at a linear relationship because our differences are not constant. So with a relationship like this, we have to sort of look for a different relationship. So in this case, we're not going to look at our delta column. We're going to look at a ratio column. So we are looking at a multiplicative or a division relationship going on between these numbers. So once we shift our focus to that, we can then see a very easy to deal with relationship between these numbers. These numbers make a lot more sense now that we're thinking about division and multiplication instead of addition. So in this case, if I look at multiplication from 2 to 6, I know that is a times 3. And 6 to 18, that is also a times 3. From 18 to 54, that's times 3. And in case you didn't know, 54 times 3 is 162. But if you didn't, the way that you could find that and verify it is to take this number divided by that number. We should get 3. This is a times 3 relationship. So this is an exponential relationship, and the way that we can tell is because it has a constant ratio, not a constant difference. So the first thing we're going to talk about is explicit form. So with this form, it kind of takes on a little bit of a different take than our linear relationships, which we should expect. It's not going to look like a linear function. It's an exponential function. So the way that explicit form works is we have f of x is, or y equals, f of x is a times b to the x power. And this is just what an exponential equation looks like. So in this case, a and b are going to be constants, and these are numbers that we're going to have to find. Now, some of this stuff is actually really easy to find once we have our table filled out. In this case, our b term, this is our constant ratio. This is the number that we're multiplying by every time. This is what goes with the x as the exponent. So we're going to say this is our constant ratio. This is what we were dividing or multiplying by. The a term, this is the output at x equals 0. So in this case, our a term is going to be 2, because that's our output at x equals 0. So all of this information for the explicit form, if we have the table, we can just read it from the table directly. So our function, in this case, the explicit form of this function, is going to be f of x is equal to 2 times 3 to the x power. If we want to verify that, we have some information here. Let's find f of 2. That would be 2 times 3 to the second power, because we're substituting 2 in for x. So in this case, f of 2 is going to be 2 times 3 squared. 3 squared is 9 times 2, that is 18. And this is verified from our output in the table. We can verify all of these if we want to, but we don't have to go through all of them. We can check it for one and say, okay, it looks like that works. Maybe we could check it for two of them. But it doesn't matter how many you try for this one, because this form works. Now, the nice thing about explicit form is if I wanted to find, say, the 100th value in this table, I don't have to also know the 98th and the 99th and the 97th and all of those other ones leading up to that one, like you would for the recursive form. So recursive form looks a little bit different, and we kind of have a general form for that as well. So our recursive form is going to look a little bit different. So we have kind of our general form here, f of x is equal to... Now the first thing we have to do is sort of begin this pattern. So we're going to start this with our first output, and we'll say if x is equal to our first input, and for this next part, we're going to take our ratio, which I called sort of this division sign, our ratio times the previous output, so f of x minus 1, and that is if x is greater than our first input. So whatever that ends up being. So for the recursive rule, it's actually fairly straightforward. It just looks really awful. Recursive rules look like they're really terrible, but again, these recursive rules are just concepts that we already understand. We know what's happening with this recursive rule. It's just taking the previous output and multiplying it by 3. And then you take that output and multiply that by 3. And then that and multiply that by 3. And that's all that you're doing. That's all that this is saying, is you start somewhere and then you multiply it by a number, but you take the previous output, multiply it, and then you get the next one. And then you just start all over. And that's sort of the recursion, is this becomes that, and then becomes this, and then becomes that, and so on and so forth. So our recursive rule for this particular function is f of x is equal to, our first output was 2. We'll say if x is the first input, which is 0. And for the rest of this, we're going to say 3 times f of, now this was our constant ratio, was 3, x minus 1, so that's the previous output, if x is greater than 0. And that's all we have for the recursive rule for an exponential function. If you have any questions, comments, points, clarification, please post those in the comments below. Otherwise, thanks for watching.